Today we're going to look at this really nice floor equation. And so we're going to, in fact, consider the equation, which is the floor of x times x squared plus 1 equals x cubed. And we have two goals. The first is to show that in between any two positive integers, there is exactly one solution. And then we're also going to show that each solution is irrational. Okay, so let's get to this first bit. So what we're going to start by doing is we'll write x as n plus epsilon. And here n will be a natural number and epsilon will be some real number between 0 and 1. And we're doing that because if we take the floor of x, we get n. Okay, so now let's take our equation. So we've got the floor of x times x squared plus 1 equals x cubed. And let's see what happens to the left hand as well as the right hand side of this equation. So this left hand side is going to turn into n because of the floor of x part. And then here we're going to have n squared plus 2n epsilon plus epsilon squared plus 1. That's from squaring out that n plus epsilon. And then over here on the right, n cubed plus 3n squared epsilon plus 3n epsilon squared plus epsilon cubed. So that's from multiplying out that n plus epsilon cubed. And now let's start simplifying some things. So n times n squared is n cubed. That gives us exactly 1n cubed on both sides of the equation. And then we've got some other like terms. So observe that this n times this 2n epsilon will give us something like this 3n squared epsilon. And then pretty similarly, this n times this epsilon squared will give us something that can be combined with this 3n epsilon squared. So now putting that all together, we've got this cubic equation for epsilon. And that cubic equation looks like epsilon cubed plus 2n epsilon squared plus n squared times epsilon minus n equals 0. And now, well, let's observe that our first part here is equivalent to showing that there's only one epsilon that satisfies this equation. One epsilon between 0 and 1, I should say. So let's maybe go ahead and set this expression equal to f of epsilon. So we're defining this function here. And then from there, I want to notice a couple of facts. And these facts will take us to the end of this first part. So let's observe that f evaluated at 0 is equal to minus n, which is negative. And then f evaluated at 1 is equal to, well, let's see, we'll have 1 plus 2n plus n squared minus n. But now we can combine some things here, and we'll see that we have n squared plus n minus plus 1, I should say, and that is positive. So here we've got f is negative, here we have f is positive. So that tells us that there's at least one solution on our interval. Now we have to show that there's exactly one solution. And we'll do that by looking at the derivative with respect to epsilon, which is of course equal to 3 epsilon squared plus 4n epsilon plus n squared. But that's clearly positive for all values of n, all natural number values of n. So just as a little outline of what this thing looks like, so let's say here is 0 and here is 1. So we know over here at 0, this function is negative, so perhaps it's right here. Over here at 1, this function is positive, so perhaps it's right there. And then it's increasing. So if it's increasing, that means it can only cross this x-axis exactly one time. And that time would be right here. Maybe that's at the point epsilon naught or whatever. So all of this tells us that there is a unique epsilon naught on the interval from 0 to 1. Notice it cannot include 0 by this fact right here, such that f of epsilon naught equals 0. But that unique epsilon naught is exactly what builds our unique solution on that interval here from n to n plus 1. Okay, so we've taken care of this first bit. Now let's look at the second bit. Okay, so for the second part of this problem, we want to show that all solutions to this equation are in fact irrational. We just showed that there was a solution between any two natural numbers. Now we've got a little bit more to show. So we're going to do this by way of contradiction. So by way of contradiction, let's suppose that we've got something that I'll call R, which is a rational number, such that the floor of R times R squared plus 1 equals R cubed. Okay, but now what we'll end up doing is we'll write R as a natural number plus A over B. Well, of course, before we wrote it as a natural number plus epsilon, where epsilon was a real number between 0 and 1. But now, in order for R to be rational, this bit between 0 and 1 also has to be rational. Furthermore, we can impose some conditions on A and B. So here we need B to be bigger than A, and that's just to ensure that A over B is less than 1. And then we need A to be bigger than or equal to 1. So that's just to ensure that, well, it's positive. And then furthermore, we might as well take these two numbers to be relatively prime. So in other words, our fraction is in lowest terms. Okay, so now what we'll do is take our expression for R and we'll plug it into the equation which is satisfied by this expression for R. And well, after doing exactly the same sort of calculation that we did before, we pretty quickly end at the following equation, and that is A cubed over B cubed plus 2 times n times A squared over B squared, and then plus n times A over B, that should be n squared times A over B equals n. So that was simply replacing that A over B, or that epsilon, with A over B. Okay, but now let's observe that we can rewrite this kind of solving for A cubed. And we'll see that A cubed is equal to, well, when all is said and done, it's going to be a multiple of n. When we move these last two terms to the right-hand side of the equation, they both have a multiple of n. The thing that's there already has a multiple of n. And when we clear the denominator, well, it's still a multiple of n. So I'm going to write this as m times n for some natural number m. So, like I said, A cubed is a multiple of n. Now what we'll do is flip this back into our equation that we just wrote down. And let's see what that's going to turn into. We'll have mn over b cubed. So that's just doing our replacement of A cubed with m times n. And then, well, everything else is going to stay the same. So I'll just copy that down. So n squared A over B equals n. Now, let's observe that everything in this equation has a factor of n, which gives us the opportunity to do some simplification. I can divide by n. That's going to get rid of this. It's going to get rid of this. It's going to take this down to an exponent of 1, and it's going to turn this into the number 1. And then, well, we can move some things around in an elementary way to see that m is equal to b cubed minus 2a squared b, and then plus nab squared. But then the important thing here is that this is equal to b times some number. So I'll write this as b times k. Okay, great. But now let's observe that that tells us that b divides m. But then up here, we see that also that m divides a cubed. So putting these two things together, we see that b divides a cubed. But then also fairly clearly, b divides b cubed. So what that tells us is that b divides the GCD of a cubed and b cubed. So if it divides both of them, it's a common divisor. But if it's a common divisor, divides the greatest common divisor. Oh, but look up here. The GCD of a and b is 1, which implies fairly quickly that the GCD of a cubed and b cubed is also equal to 1. But that means that we have b divides the number 1. But the only way to divide the number 1 is for b to be equal to 1. But then up here, we see that putting these two things together, that b is larger than 1. And that's our contradiction. We simultaneously have that b is equal to 1 and that b is bigger than 1. So what did we contradict? Well, this assumption way up here that there was a rational solution to our equation. And that's a good place to